NASA has captured the highest resolution images yet of interstellar visitor 3I Atlas, but they haven't released them to the public. Two sources have confirmed to Harvard physicist Avi Loeb that the space agency plans to make these images available in the middle of next week. These aren't just any images. They were taken from the side of the object when it passed within 29 million kilometers of Mars on October 2nd, offering an unusual opportunity for detailed observation that we won't get again. The delay in releasing these crucial images has sparked discussion in the scientific community. NASA officials have stated that the images required processing time before public release. The recent government shutdown may have contributed to additional delays. Professor Loeb, who heads the Galileo project at Harvard, prefers to believe the processing story rather than consider other reasons for the withholding of these images. The scientific community continues to wait with anticipation for what could be the most revealing look yet at this mysterious interstellar visitor. What makes these unreleased images particularly significant is what astronomers are already seeing in current observations. The object's tail has returned in the latest images, and more remarkably, 7 distinct jets are shooting from it. These aren't random emissions. Some jets emerge specifically from south of the central object. Some point directly toward the Sun, while others spray away from it in the opposite direction. This coordinated pattern doesn't match typical comet behavior, where outgassing usually follows predictable patterns based on solar heating and rotation. Professor Loeb finds the coordination of these jets deeply surprising, given what we know about the object's rotation. The object rotates once every 40 to 60 hours based on the latest measurements and analysis. This rotation period has been confirmed through multiple observations. Given that rotation speed and the typical velocity of material flowing from comets, you would expect these jets to be smeared across the object's surface over a period of approximately 1 month. The material making up these jets should spread and blur as different parts of the object rotate into and out of sunlight. Instead, they remain tightly coordinated and distinct, maintaining their structure in a way that challenges our understanding of cometary physics. The physics problem becomes clearer when you consider how comets normally work. As a comet approaches the Sun, solar radiation heats its surface. Volatile materials like water ice, carbon dioxide, and other frozen compounds sublimate directly from solid to gas. This creates jets of vapor that carry dust particles with them. As the comet rotates, different areas of the surface face the Sun, creating new jets while old ones fade. Over time, this process should create spiral patterns or diffuse halos around the object, not the tight coordinated streams we're observing with 3I Atlas. 3 hypotheses could potentially explain this unusual jet pattern, though Professor Loeb emphasizes that none are confirmed and all remain speculative. The first possibility is that only specific pockets of the surface that face the Sun are getting warmed up enough to produce jets, while jets also appear going in the opposite direction away from the Sun. This would require an unusual surface composition or structure that concentrates volatile materials in specific locations rather than distributing them across the surface. The second hypothesis suggests the object might have broken apart, with the jets representing trails of material streaming from fragments flying outward. This would explain the multiple jets and their coordination if each fragment produces its own trail. However, this explanation faces a significant problem. The latest dimensional imaging shows what appears to be a single coherent object in the middle, not the cloud of fragments you would expect from a breakup event. The object appears to maintain its structural integrity despite producing these unusual jets. The third hypothesis, and this is where Professor Loeb's analysis becomes most thought-provoking, proposes that these could be thrusters from a technological object. Such thrusters would be used for maneuvering and navigation in space, potentially maintaining orientation as the object travels through our solar system. While this remains highly speculative and unconfirmed, Loeb argues it deserves consideration alongside natural explanations, given the accumulation of anomalies that standard comet physics struggles to explain. The case for 3I Atlas being something extraordinary doesn't rest on the jets alone. Professor Loeb has systematically documented 20 distinct anomalies associated with this object. He has made this list publicly available on his website for scientific scrutiny and peer review. Each anomaly represents an observation that doesn't fit neatly into our standard models of how comets or asteroids should behave. While any single anomaly might have a conventional explanation, the combination of 20 unusual characteristics demands careful investigation. 2 anomalies stand out as particularly compelling in Loeb's analysis. First, the object aligned with the plane of the planets from the very beginning of its observed trajectory through our solar system. This is unusual because interstellar objects should approach from random directions. The vast majority of space lies outside our solar system's ecliptic plane, so an object arriving from interstellar space has no reason to align with our planetary orbits. The probability of such alignment happening by chance is low, though not impossible. The second major anomaly concerns the object's mass. 3I Atlas is much more massive than astronomers expected for an interstellar visitor. Previous interstellar comets that models predicted would visit our solar system were calculated to be 1,000,000 times less massive than what we're observing. This isn't a small discrepancy that might result from measurement error. It's a fundamental difference that suggests either our models of interstellar object formation and ejection are seriously flawed, or 3I Atlas formed through an unusual process we don't yet understand. The mass anomaly has profound implications for how we interpret all other observations. Larger objects behave differently than smaller ones in space. They retain heat longer, can maintain structural integrity under greater stress, and require more energy to accelerate to interstellar velocities. If 3I Atlas is indeed as massive as observations suggest, it challenges our understanding of how objects get ejected from their home solar systems and achieve the speeds necessary for interstellar travel. The scientific community remains deeply divided on how to interpret 3I Atlas. Physicist Michio Kaku recently provided his assessment when asked directly about the possibility of alien origin. He stated clearly that while the probability of it being alien in nature is not zero, he considers it very small. Despite acknowledging a few anomalies, Kaku maintains that the object fundamentally acts like an ordinary comet. His position represents the mainstream scientific view that extraordinary claims require extraordinary evidence, and that natural explanations should be exhausted before considering more exotic possibilities. Professor Loeb's response to this mainstream position is direct and challenging. He argues that anyone claiming this is an ordinary comet should write a comprehensive scientific paper explaining all 20 anomalies. The burden of proof, he insists, should work both ways in science. Those asserting that 3I Atlas is a normal comet should demonstrate how standard cometary physics accounts for every unusual observation. Simply dismissing anomalies or explaining a few while ignoring others doesn't constitute rigorous science. This debate between Loeb and Kaku represents more than a disagreement about one object. It reflects different philosophical approaches to anomalous observations in science. Kaku's approach emphasizes caution and the principle that familiar explanations are usually correct. Loeb's approach emphasizes following evidence wherever it leads, even if that means considering unconventional possibilities. Both perspectives contribute value to scientific progress. The timing of NASA's image release becomes increasingly critical as 3I Atlas continues its journey through the solar system. Each passing day takes the object farther from optimal viewing positions. The October 2nd encounter with Mars at 29 million kilometers represented a unique opportunity that won't repeat. Those images captured details that Earth-based telescopes, no matter how powerful, cannot replicate due to atmospheric interference and distance limitations. The images were specifically taken from the side of the object, which provides crucial information about its three-dimensional structure. Previous observations have primarily shown the object from behind or ahead along its trajectory. Side views can reveal whether the object is elongated, whether it has irregular features, and whether the jets originate from specific structural points or emerge randomly across the surface. This geometric information is essential for testing different hypotheses about the object's nature. Processing astronomical images from spacecraft involves complex procedures that genuinely require time. Raw data arrives as digital signals that must be reconstructed into images. These images need calibration against known standards, correction for instrumental effects, and enhancement to reveal scientific details without introducing artifacts. NASA's stated need for processing time before release likely reflects these genuine technical requirements rather than bureaucratic delay. The scientific method demands patience and careful analysis, especially when confronting genuinely puzzling observations. Rushing to conclusions, whether dismissing all anomalies as measurement errors or immediately embracing exotic explanations, undermines the scientific process. Each anomaly needs individual investigation while also considering how they might relate to each other. Patterns in the anomalies might point toward specific explanations that wouldn't be apparent from examining them separately. Professor Loeb's approach treats the investigation like a detective story, where the ending remains unknown. This isn't just colorful language, but a fundamental principle of scientific investigation. Like detectives, scientists must gather evidence, form hypotheses, test those hypotheses against new evidence, and remain willing to revise their conclusions as new information emerges. The key is maintaining objectivity and avoiding premature certainty. The coordination of the jets presents specific physics challenges that deserve detailed examination. In a normal comet, volatile materials are distributed throughout the nucleus, mixed with dust and rock. As sunlight heats the surface, these volatiles sublimate wherever temperatures rise sufficiently. The rotation of the object means different areas receive sunlight at different times, creating a complex pattern of activation and deactivation across the surface. For jets to remain coordinated as observed with 3I Atlas, several unusual conditions would need to exist. The volatile materials would need to be concentrated in specific regions rather than distributed uniformly. These regions would need to maintain their jet production despite rotation, perhaps through unusual thermal properties or depths that buffer against temperature changes. Alternatively, the jets might originate from deep within the object through cracks or vents that maintain consistent orientation. The observation that some jets point toward the sun while others point away adds another layer of complexity. Solar, radiation, pressure, and heating should primarily drive material away from the sun. Jets pointing toward the sun would require either unusual internal pressure dynamics or possibly active propulsion. This bidirectional pattern doesn't fit neatly into standard models of cometary outgassing. The rotation period of 40 to 60 hours provides another piece of the puzzle. This relatively slow rotation for an object of this size could result from several factors. The object might have lost angular momentum through previous interactions. It might have an unusual mass distribution that affects its rotation. Or, as Loeb's technological hypothesis suggests, the rotation might be controlled for specific purposes such as thermal management or navigation. When examining the possibility of artificial origin, it's important to consider what evidence would definitively support or refute this hypothesis. Artificial structures might show geometric regularities not found in natural objects. They might contain materials or isotope ratios not typical of natural solar system formation. They might exhibit behaviors like course corrections or responses to stimuli that natural objects wouldn't display. The upcoming NASA images could potentially reveal some of these characteristics if they exist. The scientific community's response to 3I Atlas demonstrates how science handles genuinely anomalous observations. Rather than ignoring inconvenient data or forcing it to fit existing theories, good science adapts to accommodate new observations. This might mean modifying existing theories, developing new models, or acknowledging that we don't yet have adequate explanations. The process is messy and uncertain, but ultimately leads to better understanding. The mass anomaly deserves particular attention because it affects so many other aspects of the object's behavior. An object 1,000,000 times more massive than expected doesn't just represent a quantitative difference, but potentially a qualitative one. It might indicate a completely different class of object than previously observed interstellar visitors. It might suggest formation mechanisms we haven't considered, or it might point to measurement errors that need correction, though the consistency of observations makes this less likely. Consider what we expected from interstellar visitors before we started detecting them. Models suggested they would be small objects, perhaps chunks of rock or ice ejected from forming solar systems through gravitational interactions. They would arrive from random directions, with velocities reflecting their ejection mechanisms. Their compositions would mirror those of comets and asteroids in our own solar system, formed through similar processes around other stars. 3I Atlas challenges several of these expectations simultaneously. Its alignment with the planetary plane suggests either remarkable coincidence or some form of trajectory control. Its mass exceeds predictions by 6 orders of magnitude. Its jet patterns don't match standard cometary behavior. Each deviation from expectations provides information about either the diversity of interstellar objects or the limitations of our current models. The comparison with Oumuamua, the first confirmed interstellar visitor, provides important context. Oumuamua displayed its own set of anomalies, including unusual acceleration without visible outgassing, an extreme elongation, and unusual tumbling motion. Now 3I Atlas presents different but equally puzzling characteristics. Together, these objects suggest that interstellar visitors might be far more diverse and unusual than we anticipated. Professor Loeb emphasizes that keeping an open mind doesn't mean abandoning scientific rigor. Every hypothesis, whether conventional or exotic, must be tested against observations. The technological hypothesis makes specific predictions that can be verified or falsified. If the jets are thrusters, they should show consistency in thrust levels and directions. They might activate at specific solar distances. They might exhibit patterns related to trajectory optimization rather than simple thermal response. Natural explanations also make testable predictions. If the jets result from concentrated volatile pockets, spectroscopic analysis should reveal varying compositions from different jets. If the object is beginning to break apart, subsequent observations should show increasing fragmentation. If unusual thermal properties cause the jet patterns, detailed thermal modeling should reproduce the observations. The role of skepticism in science is crucial, but must be balanced with openness to new possibilities. Kaku's skepticism serves the important function of demanding high standards of evidence. Loeb's openness serves the equally important function of ensuring we don't dismiss genuine discoveries because they don't fit our preconceptions. Science advances through this creative tension between skepticism and speculation. Public interest in 3I Atlas goes beyond scientific curiosity. The possibility that we might be observing technology from another civilization touches on fundamental questions about humanity's place in the universe. Are we alone? Have other civilizations achieved interstellar travel? Could we detect their artifacts passing through our solar system? These questions deserve serious scientific investigation regardless of what the answer turns out to be. As we await the release of NASA's high-resolution images, astronomers worldwide continue monitoring 3I Atlas with every available instrument. Ground-based telescopes track its position and brightness. Spectroscopes analyze the composition of its jets and tail. Radio telescopes search for any unusual emissions. Each observation adds data points that help test competing hypotheses about the object's nature. The importance of the Mars encounter images cannot be overstated. At 29 million kilometers distance, Mars provided a relatively close vantage point compared to Earth's position. The images taken from the side will reveal structural details invisible from other angles. They might show whether the jets emerge from specific points or broad regions. They might reveal surface features that explain the unusual activity. They might even show details that nobody has predicted. The middle of next week deadline that Loeb's sources provided for the image release will mark an important moment in the investigation. Whether these images resolve the mystery or deepen it, they represent our best opportunity to study this interstellar visitor in detail. The scientific community and interested public alike wait to see what secrets these images might reveal. The scientific process unfolding around 3I Atlas exemplifies how we expand human knowledge. We observe something unexpected. We document anomalies carefully. We propose multiple hypotheses. We gather more data to test these hypotheses. We revise our understanding based on evidence. This process, though sometimes slow and uncertain, has proven remarkably successful at revealing the universe's secrets. Professor Loeb's call for colleagues to explain all 20 anomalies comprehensively represents good scientific practice. It's not enough to explain away a few unusual observations while ignoring others. A complete theory must account for all the data. If standard cometary physics can explain everything we're seeing, someone should demonstrate this systematically. If it cannot, we need to consider alternatives. The verdict on 3I Atlas remains genuinely open. Claims of certainty in either direction, that it's definitely natural or definitely artificial, aren't scientifically justified based on current evidence. What we can say is that this object displays characteristics that challenge our current understanding and demand explanation. Whether that explanation will ultimately be conventional or revolutionary remains to be determined. The investigation of 3I Atlas continues as the object proceeds on its path through our solar system. Each day brings new observations, new analyses, and new questions. The jets continue their coordinated display. The object maintains its trajectory. The anomalies persist, and scientists worldwide work to unlock the mysteries of this remarkable interstellar visitor.